All right, let's get started. And the prompt, as a reminder, is general reactions plus what variable can you trade off against latency, and what's an interesting example of latency in a distributed system. Why don't we start with Sachin today and go up?
Yeah, hey. Yeah, I don't have much thoughts on the wiki article. I did read what Ben said about proof of stake versus proof of work. I didn't quite catch how latency is important in that. So it would be nice to hear more when Ben gets a chance to talk. But I was thinking of latency in like distributed systems. And I was thinking of systems in which and I don't know if this can be called latency, but like latency is built in irrespective of like technology advancing. Like the US visa process is one where a lot of things are like mail, like you have to physically mail things, and there's a purposeful it's made obscure. Like a lot of things are made obscure to you with respect to like where you are in the queue or queue of things to be processed. So all of that is not sometimes clearly communicated to you. So like a lot of things are purposefully there's like information asymmetry there, and it seems pretty purposeful to like make people like latency that is built in to make people work as much as possible to get a visa or a green card or whatever. So I was thinking of more examples of that. While I guess the opposite example of that is the Silicon Valley bank run, where I guess the part of the reason why it was so quick was that because you had technology where information could spread with low marginal cost pretty fast, and people could withdraw money pretty fast. Yeah, that's all for now. I'll come back later. Jenna?
Yeah, I saw your post thinking about it's not a great article. But, so coming as a liberal arts person, it's kind of like, this world needed a fancy word for the general thing things take time, because so much of computing really does feel like there's no time involved at all. So the instancy of so much of what we get. But so every time you have a delay, it's sort of shocking. And I remember one of the early pieces of guidance for making sure your eyes aren't wrecked by using screens is every time you're in fact find yourself waiting with some sort of a progress indicator to look away and or blink. And so as a way of building in eye rest during your computing sessions. So that whole piece is kind of interesting to me. And then a couple of other quickies. I couldn't find it, but there was a quality that I remember from economics with end station costs is what I remember it was called, though as when I tried to Google that up, it gave nothing. So the time it takes to go between points is one thing, but the time it takes to process the thing once you get there, and the easiest real world examples, like how long it takes you to load your car versus how long it takes to drive somewhere versus then unload your car again. So there's a time element there. How long does it take for the bit to get processed once it lands where it gets? I didn't see that addressed, but it's a part of it to me. Another piece was that whole arms race for trading floors. I remember it was probably a New York article, but just there was a real rat race to build closer and closer so that your pipes to the trading floors were shorter, because at that level of volume, milliseconds mattered. So that's an interesting piece. And then the third thread for me has been I carry on sort of three novels in my head where the novel includes some sort of near future or far future idea where it's kind of like with the Apple goggles thing just now, but like you can have information from the internet. It's not even called needs doesn't even need to be called the internet anymore, right? Like it's not separate. And just out there in the world, you can walk around in a sea of information. But what I don't think any of these novels, I'll drop links to them in the chat. But none of them actually talk about this idea of how long it takes for that information to filter through. And then, they don't really get at the hardcore part about how do our brains react to being walking around in a sea of information. So, part of the fun of hanging out in Yak Collective is it adds new information to the sea that I walk around in. And so, jury's still out on how to use that information well. And then the third novel that I'll drop a link to, it's actually very far future. And so interplanetary, intergalactic settlement has happened. And so it's this part of the story that these galaxies communicate through wormholes now. But there again is no specific discussion of the latency for wormhole communication. So who's after me? Passing up to Grigori.
For me, the definition of latency that Wikipedia article uses is not very good. I typically think about latency in somewhat similar to what is written about Hasbrook and Saar measure of latency. I will remind that there are three components. The time it takes for information to reach the trader, then the trader has to process the information and make a decision. And after that, the action should be implemented. So it's three components instead of just one, a gap. Defining latency is a gap is not useful because there's always a gap. Anything you can observe or anything you can do contains a gap. So much more interesting to include a human in a loop. Because it helps you kind of understand there are many ways to deal with latency. For example, you can shorten the time to reach the human, or alternatively, you can train a human to start working on a different cadence. So latency can beat you up because of the cycle time. You expect something to happen, it doesn't happen, and you have to wait until a signal reaches you. This is what it's all about. And of course, human can contribute to the latency. Now, the only example I can discuss here is, in my view, any decision-making process in large organization has this latency problem. For example, some decision-making body can successfully process high priority decisions. Typically, they do because the decisions are high priority. But mid to low priority decisions are typically fall through the gaps. And it leads to a certain feeling inside the organization that nothing is really happening, decisions are not made. And again, typically you can solve this problem by speeding up email delivery to your executive or whatever. There are completely different ways to speed it up, and they have typically nothing to do with speeding up the delivery. You need to do something with humans who don't make the decision when the decision is needed. That's basically all I have, and I will pass it on to Ben.
Yeah, so when you started talking about latency, my mind immediately wandered to this, not sure what to call it, the weak subjectivity time period. Here, and I'll drop a couple of what I consider founding documents. Basically, one is a paper from 2015, basically arguing that proof of stake is impossible in a distributed system, and one is the 2014 article from Vitalik about proof of stake, how I learned to love weak subjectivity. And what I find so interesting about this argument is that the technicals, did I put that in the right place? I think I might have dumped it in the wrong chat box. Yeah, hold on. That was supposed to go in the thread. Anyway, it all boils down to the fact that in a proof of stake system, if you want to defend against long range attacks and generate some more true finality, what you have to have is you have to have a parameter in which you assume that all nodes are effectively in sync. We're going to call that the weak subjectivity time. Now, what's so fascinating about this parameter is that it's not like, I don't know, 10 seconds or 10 minutes. The weak subjectivity parameter, I mean, I don't quite know if it's a single parameter now in a theory. In the ETH2 that actually exists, I think it's dynamic. It's effectively the withdrawal time. So if you do a withdrawal, like a full withdrawal to shut down your validator, you have to wait a period before you can actually get your coins, and that's the time period. Sort of like the withdrawal time. I think in the beginning it was going to be measured in like 2 weeks or a couple months maybe, but we're talking about a delta on the order of weeks or months. I mean, you could even push it into years, but and that sort of like that withdrawal time is actually really important because that is the time period that protects you from certain attacks. In particular, if you have a bunch of coins and you're staking them, you're generating blocks, then you do a withdrawal. You withdraw your coins from the validator. Then you sort of roll back the system locally to when you had coins, fork off, and then create a competing chain. That triggers a slashing event. But because you've already withdrawn your coins, you can't be slashed. So suddenly you've basically you've dodged the economic finality part and can attack the system freely. And so that's why that time has to be significant. And you see, read the paper by basically what I call the Bitcoin side, is arguing that this parameter really should be infinite. In a truly distributed system, you're making a strong assumption that there is no time for which everyone can agree necessarily. It could be weeks, could be years. And if you make that assumption, then a lot of these proof of stake systems have problems. And I think it's very interesting because this is a technical discussion, but it's really about the overall social system that's sort of being built here. Because I mean, the thing about proof of work is that the sort of the subjectivity time is infinite in the sense that the work doesn't change. If you've done the work, you can prove it. It doesn't matter if you did that a million years ago or not. Of course, this does mean that the system can never truly come into finality. It's all probabilistic because hypothetically, people in Alpha Centauri could be building their own Bitcoin blockchain, and then in a year later or two, when it comes to you find that the last year of blocks are reorged out. So and see the argument comes to whether is that acceptable? Is that what you want to design the system? Because if it's not acceptable, then you've already effectively put in sort of this maximum reorg time, sort of by hand or by social And at that point, there isn't as much big of a reason to burn, real resources to generate hashes, since you and the argument keeps going around to stuff like people have to get their nodes from somewhere. They can't just magically create a Bitcoin node by concentrating at a screen. They have to download their nodes from somewhere. And if they're downloading their nodes, and that of course can be corrupted or can be attacked, or you can get malware or whatever from that. But if you're already having to trust that, then if that has a checkpoint in it, is that really like catastrophic to the system? I don't know. This is a very large body of work that's gone back and forth. But to try to sum it up a bit more, because I think I've probably lost a lot of you in the weeds. There is this variable, which is sort of like the weak subjectivity time, and it really defines if you're making it. When does the technical system of a blockchain roll over to the social system of the blockchain, where you have people who sort of agree that, all right, yeah, the hash of the Ethereum block a year ago was such and such, and everyone can agree, and there's complete consensus on that. And that's just that could be done socially. I mean, you could imagine Ethereum where with one block per year, and everyone just at the 1st of January competes to make their block. And then by the end of the year, after endless emails back and forth, people have all agreed that one of these blocks is a winner. So that part doesn't actually require a consensus algorithm. That could be done by hand. It'd just be way too slow. No one's going to be waiting a year for the transaction to be confirmed. And the whole point of a blockchain system is you have this sort of code underneath, sort of powering, making the system go 24/7, making it go fast, making it so you can interact quickly. But it's where at some point the code gives way to a social system that humans can actually, use their slow human brains and deliberations and forum posts and talking to actually come to consensus. And the blockchain just sort of acts as a bridge from like the second or the sub-second time scale to the human time scale. And questions about sort of consensus mechanisms and all these technicals come down to how should that bridge be designed? What are the real weak points of it? What do we have to worry about? At what point is social, like how much can we trust the social level to be fast? How much can we trust to be agreed? Bitcoiners tend to take a very low view of the social layer. Possibly and from some of the maximalist positions of it doesn't even exist, which I would argue is very inconsistent. But you can push the argument that the social layer needs to be handled in less and less. Whereas you can also push the argument the social layer can be handled more and more, and I actually think you can do that too much. You end up with almost completely trusted system without economic finality at all. But anyway, I think I've blabbed on long enough. I just find it's very interesting that this huge social discussion ends up coming down to whether a time is finite or not. And the time in question is not even like the time for two computers to talk to each other or the time to send an email. It's like this sort of large abstract time of coupling between the social system and a technology.
Thank you. I thought the article was good in that it was a very high level definition of what latency is, and I like that they sort of showed it in the application of latency in different areas. So I try to sort of understand my definition of what latency is. I came back to this sort of observable time delay between a cause and an effect. So that to me sort of explains latency across a lot of different applications. One place that my mind immediately went to was like if you in fluid dynamics, if you have some liquid flowing through a pipe, you would sort of the latency, if you can think of it that way, is could be the time it takes for fluid to go from point A to point B, but it is a function of, especially in the case of flowing through a pipe, it is a function of two different things. One could be the viscosity of the fluid itself, so it's just like an internal friction of the fluid itself that's that causes some time delay as it wouldn't in a perfect fluid. And another one is sort of an external friction of the pipe surface itself. Again, that could cause some sort of delay, time delay, and how long it takes for fluid to go from point A to point B. So it seems, at least in that example, and I sort of try to think of it abstracted from there, it seems latency is both in sort of the function of the medium and also the function of the environment the medium is operating in, and again the sort of the unifying function between those two things is the friction, either internal or external. Another area that my mind went to is the sort of typical problem associated with macroeconomics, where there is a time delay between, like say, a policy action and the effect of that policy action in the economy, and there is a constant sort of fight between. There's a constant fight in that loop, and it's hard to measure the sort of changes in the economy, for example, as a result of some policy action. So there's another area that my mind sort of went to. So and I think it was such a, like Venkat sort of summarized it as, like, latency could be an hostile design function or could be used to your advantage. So again, I think of friction there. Like, friction is not always a bad thing. Sometimes you use friction to your advantage to design some systems or some some surfaces. And again, it's a function, like I think Jenna said that sometimes in software also the latency could be used to enhance a user experience sometimes. And again, like, one last thought on latency was, like, all this vision, like all this latest updates from Apple on spatial computing, or whatever vision was they call it, is my mind kept going to latency as a problem between, like, an application running and what we can perceive as a result of it. Because oftentimes when I've tried these devices before, I always end up nauseated or just not able to continue it for a long time, and that often is a result of latency between different images or different screens moving around in these sort of virtual environments. So that's all I had. I'll pass it to Venkat.
Yeah, this is a topic that's very interesting to me, since I have a long-standing interest in time, and I'm working on my second book about time. But I've surprisingly never stopped to really think about latency in the broad sense, even though in, like, specific narrow technical senses, it's obviously been important in control theory. Time lags in feedback loops are kind of an important thing you worry about. But latency in general across categories is something I've never really stopped to think about. And it suddenly struck me this morning that it's kind of a very general feature of all complex systems that you have to think of and trade off against other things. So just answer my own prompt. An interesting example of latency effects is last couple of days we were driving around quite a lot in the Seattle area. There's lots of islands here connected by ferries. And one of the interesting things about ferries is there's a couple of different sizes of ferries that can hold different numbers of cars. So there's a big and a small ferry, I think. And each of the islands, their port terminal or ferry terminal has a parking lot with rows of cars waiting to board the ferry with different capacities. So they're not always exactly the same. So you might have, like, 10 rows of cars, each with, like, 10 capacity, giving you a total 100 car buffer capacity or something. But it doesn't always match the ferry capacity properly. And on busy times, invariably the ferry queue kind of, like, overflows the lot and sort of extends up the street. And if you're trying to catch the ferry, usually, and you arrive, say, 20 minutes to half an hour before the ferry, you end up joining the end of the queue that's spilled out of the lot, maybe almost like half a mile or more up the street. And you never quite know whether you're going to make the ferry, because you don't know how big the boat is going to be and how long the queue is in front of you. And it's always like a little bit of a guessing game. So last couple of days, we got lucky and unlucky in both ways. Like, at one time, we thought we weren't going to make it, but because the lot was full, we were actually on the boat, but we didn't realize it because they were waiting to like load the existing boats before they would let us on, and you to pay and join. So when we actually paid for our ferry ride, we drove right onto the boat instead of to the waiting lot. So that one example. Another example, we were waiting and we thought we would make it because we had plenty of time, but we were just one car short. So like the car ahead of us got cut off, and then we were number 2 in line for the next ferry, and that was delayed. So the point is, the lag had an uncertainty equal to the ferry frequency. So in the first case, we ended up getting on the ferry 30 minutes earlier than we thought, and in the second case, we ended up waiting like more than an hour longer than we thought we would, and there was no way to tell. And while waiting, I was getting bored and thinking about like how you design a UX around this that actually tells you. Because some of the ferries do have like an online service where you can go check how full is this ferry, how many spots left on the next ferry, and so forth. But it's not updated in real time. So there's now like a information system lag added to this like physical system lag, where it tells you there's like 17 spots left on the next ferry. And I was doing things like, oh, it looks like there's more than 17 cars ahead of me, so we won't make it. But that's lagging, and it doesn't take into account this like buffer plus queue size bullshit. So it's actually useless information. So you go online and you see a number, but it tells you nothing about whether or not you're going to make it onto the ferry. So really what you need is kind of like, there's obviously a last car that's going to get onto the ferry because that's almost a hard cap. And you need kind of a marker between them where you know that you're not going to be on the 5:30 ferry, you're going to be on a 6:10 ferry or something. And it's actually a challenge UX design problem to establish that marker and communicate it to the people, because like one way to do it would be you could have a little robot car that just circles around and inserts itself into the right point in the queue as punctuation and says, at this point, delay goes from 30 minutes to 1 hour, right? But what I saw was the inadequate online system. And the other one was, as you approach the payment booth, the guy holds up a sign. So we were like 10 cars away from the payment booth, and he held up a sign saying 5:35. And we assumed it meant that boat was full, and it was correct. But it was like slightly misleading, because not all the cars that saw the guy holding up the sign should take the same message from it, because the ones almost to the front of the queue could actually get through. A couple of cars could actually sneak through, but if you were further back, that indicated that the boat was full. So just an complex example of like designing around latency. The other prompt of mine, which is what variables can you trade off? Obviously, buffer sizes are a thing you can trade off against latency. Couple of non-obvious ones. Any kind of modularity, like take a large map, which is broken up into like cellular blocks, like a cell network map or something. Anytime you're inside a cell, processing time for anything like establishing a communications link is something. But if you're crossing boundaries, then the processing time includes handoff time, so it's longer. So the act of breaking up a large complex system into like more bite-sized chunks includes like a variable processing delay. So that's something you have to trade off. So I actually ran into this problem back in the day when I was working on a robot mapping problem, where there was not enough memory to hold really large maps in memory. So to break up the map into little blocks. And each time the robot path crossed a block boundary, both the computation time would change and the computation efficiency would change, because you had to use a different algorithm for doing like the 2-level block mapping. So yeah, any kind of like block structuring of a problem creates a latency thing. I think there's also a trade-off between serialization and parallelization. And an interesting one is contingency. So imagine you're talking to somebody on a space mission to Pluto with like a 240-minute round trip delay, and you're trying to have a conversation. Now, the normal time constant for human conversation is like, interchange every couple of minutes. And normally you have a linear conversation. I say something, you reply, then I say something again. And you're not like trying to like cover all possible contingencies. But I read an article that said that if you're communicating to Pluto or something, the ideal strategy is to just talk continuously and say everything that the other person might possibly need to hear, including like, all the if-then possibilities. Like say the astronaut is repairing, I don't know, some failed system, and you're trying to help that astronaut, what should you say? So you should consider all parts of the troubleshooting tree without waiting to hear back and say, like, normally if you're helping somebody troubleshoot over, say, like a no delay system, you would say something like, oh, all right, is that fault indicator light on? If so, do X, Y, Z, like, turn off that switch. But if you're talking to somebody on Pluto, you can't wait for that. So you say something like, if the indicator light is on, then unplug that wire, but if it's not on and this other thing is on, then unplug the other wire, right? So you actually have to like basically communicate a much broader part of the contingency tree if there is delay, which tells you that the longer the delay, the more of the sort of possible world space you kind of have to inhabit, because you don't know. You're fundamentally guessing what situation or state the other end of the communication channel is. So you kind of have to like inhabit the all of possibility space. So yeah, lots of such interesting examples. And final thought I had was Sachin's point kind of got me thinking that I always think of lag as kind of like an unintended consequence and always a problem, but it's really a 2x2. Lag can be either accidental or designed, and it can be good or bad. So there's like 4 kinds of lag going on, like designed and good, designed and bad, design or accidental and good, and accidental and bad. Yeah, I'm now trying to think of like examples in all 4 quadrants. Yeah, I think that's all I had. So, all right, open floor for more comments. Oh, I had one more thought. I posted that link, which is my review of a book called 10th of a Second by Jimena Canales. And it talks about how important the human perception 10th of a second is in like lots of systems. Like, you can watch movies because vision persistence is a 10th of a second. So that's one important time constant in delays in engineering any system with human in the loop. And another important one is lifespan. So humans typically don't live beyond 100 years. So many long-lived human systems have to be designed with that time constant in mind, where there's a boundary being crossed around 100 years. So 10th of a second and 100 years.
I just recalled another example, rather interesting one from soccer. We read an article about Messi some time ago. There was another famous player and one of the best coaches and managers around called Pep Guardiola. And he has a rather famous 5-second rule. And basically this rule says when you are attacking and somehow manage to lose the ball to the other side, your best strategy is not to go back, but instead use 5 seconds to go forward and try to win the ball back. And it is based on a very simple idea that in the first 5 seconds, the opposing team is incapable of transitioning from defensive post to offensive post, from defensive formation to offensive formation. So they need this delay to transition to an offensive poster. So in first 5 seconds, basically, most likely they're unable to hurt you. And then when this first 5 seconds pass, the most natural thing you can do is just stop the clock. And you are stopping the clock in soccer by committing a foul. And this is how Barcelona and Manchester City are playing these days. They're using this little gap to make life of the opponents a little bit harder.
I'll jump in with a quickie. Relative to your Pluto example, there's a big plot point in The Martian, both in the book and the movie, where once he figures out how to communicate And then the details are vague for me now. If somebody else probably can fill in the details. But it's a big plot point where they figure out how to communicate with quite a huge time lag, as I recall. Passing back.
Yeah, I thought of another example that frequently comes up whenever you have to arrange a sequence of times in space. So I'm thinking of something like if you're like doing a series of actions in, say, a big bureaucracy where you have to maybe take a form from one booth to another booth to another booth. And so you're basically following a timed action through space. And interestingly, so this kind of thing comes up in computer processing a lot. So if each, suppose you have to take a task through 10 steps and each task takes 10 seconds and walking between the booths takes another 10 seconds, you have kind of this regular pattern of wait 10 seconds at a booth, then walk 10 seconds to the next one. And so if in such a system, all the queues will be approximately of equal length and things will be kind of like smoothly flowing. But anytime you have to kind of like respect the constraints of space, like maybe it's a square building and you can't like create an infinitely long series of booths where people can get processed, and you have to wrap it around in a matrix, like rows, like, pixels on a screen or a raster scan, then you have these interesting like interior boundary conditions where like maybe if you have like 100 points that thing has to flow through and it's arranged in a 10 by 10 matrix, then between 1 and 2, you might have a 10-second delay to walk, but between nodes 10 and 11, you might have like a 60-second time to walk, right? So you kind of have to accommodate that. So people do various strategies, like if the processing steps have like different durations, maybe you put a very short processing step at the end of a row, because that way the effective handoff time between node 10 to node 11 will be the processing time plus the walk time, and that may be equal to others. So people do a lot of like spatial time space balancing of like queue processing, and sometimes they have to like add special delay units to sort of balance the network, especially if you're like doing parallel processing where you have like 2 bits of information being processed by 2 sort of sequences of actions, and there's like physical delay between them based on the layout. And sometimes you just have to add a delay where, it's, I think, imagine it as the equivalent of 2 things have to arrive at a processing station at the same time, but because of physical layout, one would arrive earlier than the other if you didn't do anything. So you might just add like a long winding corridor to add delay. So often chip designers do that sort of thing to synchronize sequences of event streams. So it's kind of an ill-formed thought, but the trade-off there is between temporal design and space topology, I guess. And I think it applies in everything from like computer processors to city layouts and humans walking through systems, like, Disneyland or something like that. I thought of a Disneyland type example. If you go to any of the theme parks in LA, there's long queues waiting to get into any attraction. And often they try to like make it interesting by like making it winding through a bunch of exhibits. So it's like you're walking through a museum while waiting in the line. All right, a few minutes left. Any final thoughts? All right, then we'll meet again next week. And I thought in the next couple of weeks, we could take some time to review the things we've been reading for the last few months and try and map out and make some sense of where we are and what new themes we might want to discuss. We are coming up on like summer solstice next week, or this week actually. And so it's time for like a seasonal theme review and change. So if anybody has any ideas about themes you want to talk about or topics you want to cover, share in the distributed systems channel. All right, see you guys next week.